So today we're going to talk about the existence of God, one of the reasons that I believe in a maker of the universe, and it's called the Goldilocks Enigma. So have you ever heard of Goldilocks before? Who's Goldilocks? Yeah, that's right. But which porridge does she eat? There's a hot one, a cold one, and a one that is in the middle. Which one does she eat?
The little bear.
She eats the one in the middle because it's just right. So that's what the Goldilocks tale is. It's about Goldilocks and the three bears, and she chooses the porridge that's just right. It's not too hot or too cold. So this is called the Goldilocks Enigma. And I'll explain why. And I'll explain to you why it's so compelling to me. So in physics, or in the real world, there are lots of numbers that exist, right? I'm holding two markers. The number 2 is a number, right? There are some more complicated numbers like pi. Have you heard of pi? Pi.
Not the pie you eat.
No, you're right, not the pi you eat. It's a number, and it's the ratio of the diameter of, the circumference of a circle to its diameter, and that number you can derive using relatively simple math, and it turns out to be 3.141592653, and so on. That's a number you can derive. But it turns out that in physics, there's something called the standard model of physics, and that's the line of belief that we've had for the last 30 years or so in terms of what determines how things interact in the universe, how gravity works, how magnetism works, how electricity works. It's called the standard model. There are some numbers, so this is what we call pi. This ratio is pi, and that's a number that we can derive.
That's the symbol for pi.
That's the symbol for pi. It's the Greek letter pi. But there are some numbers that you can't derive. You can't just figure out. You have to measure them. One of those, go ahead.
What is derive?
So this right here, when I say derive, what I mean is I can figure out, if I spend a few hours doing math, I can figure out that this number is about 3.14. And if I work a little harder, I can find out that there's another number after that and another number after that. So I can do this by math. I'm not going to show you that, but I can do it by math. In other words, I don't need to measure anything. Believe it or not, I don't need to measure a circle to figure out what pi is. I don't have to measure anything. I can literally just do math and figure out what pi is. That's what it means to derive it. But there are some numbers that cannot be derived. Well, an example is your height and your weight, right? I can't just figure those out one day and just, on the back of an envelope and do some numbers. I can't just figure out what your weight is or what I have to measure you, right? You have to get on a scale to weigh how much you are, and you have to use a tape measure to figure out how tall you are. Does that make sense? I have to measure you. Well, it turns out that one of those numbers that you can't derive is excuse me. So you know what gravity is? You know what that is, right? It's what pulls you down to the earth. And I'll bet you know what this big word is. Electromagnetism. I'll bet you know, even though it's a complicated word, that actually is two forces combined in one. Electricity, and you know what that is, right? Plug in stuff in the wall, that's electricity. That's a force that causes things to happen. And I bet you know what magnetism is too, right? You know what a magnet is, right? A refrigerator magnet sticks to the refrigerator, okay? Well, anyway, so I bet you, so you know what electromagnetism is, and you know what gravity is. Well, how strong is gravity, and how strong is electromagnetism? Well, it turns out you can do, yeah, go ahead.
You explain electricity and you explain magnetism. What is it together?
It's electromagnetism.
How would you? We understand gravity. It's pulling us to the
100 years ago, 200 years ago, they were thought to be different forces. About 100 years ago, actually a little more than that, they figured out this actually is the same force, but I'm not going to try to convince you that or show you that. Okay, so in fact, if you prefer, let's just talk about The gravitational force and the electric force. Okay, let's just talk about those. Now, which one is stronger? Well, it turns out the electric force is way, way, way stronger.
Really? I thought
Yeah.
gravity would be.
Well, that's funny you should say it. You would think so, right? But it only takes a small magnet to cause something to levitate, right?
Yeah.
So in other words, that little magnet is overcoming the gravitational force of that object. So it turns out that the electric force is actually much, much greater than gravity. And there's a ratio. This over this is a certain amount. And the reason that matters is this. Here is the sun. And the sun is red right now because it's sunset. The way the sun works, I'll keep it simple. The way it works is this. Fusion. Fusion is when atoms come together and they create energy. That's it. The sun is full of a whole bunch of hydrogen. Hydrogen is an atom, right? It's an atom, and they fuse together to create helium. I know this is sounding complicated. It's really not. It's not too bad. Well, what happens is when that fusion, the gravity is what pulls all of that together. It holds all of it together. The gravity pulls in that hydrogen gas. But the electric force is actually pushing them apart because they're all protons and they're all positively charged. Again, this is more than you need to know. The point is that the electric force is pushing those apart, gravity's pulling them together, and they're just at the right balance so that if you had any more gravity, the sun would shrink too much. And if you had not enough gravity, then the electric force would push everything apart too much. So it's a nice balance between gravity pulling everything together, pulling the sun together, and the electric force pushing it apart.
So the sun stays the same size.
Here's why that matters. Here's why that matters. We're on the cusp of it, of Goldilocks. This ratio, when I say a ratio just means how big is this compared to how big this is, okay? This ratio happens to be a number. And I don't even know what the number is off the top of my head. It doesn't matter. It's some number. But if you make gravity just a little bit more, 1% more, just a little more, then the sun as we know it would have been much smaller, because gravity would have held it together. And because it's much smaller, it burns up its fuel way faster, which means that life could never have existed on our planet, because the sun would already be burnt out. But what if, in fact, not gravity was a little bit bigger, but what if the electric force was just a little bit bigger? A little bit bigger. Then the sun would have been enormous, and the Earth, which is out here orbiting somewhere, the sun would have just engulfed, eaten up the Earth, which means we couldn't be here. Does that make sense? So in other words, if you twist this number just a tiny bit, or this number just a tiny bit, life as we know it on this planet couldn't exist. We wouldn't be here. Isn't that weird?
We would.
Right. So one objection to this argument is that, okay, so maybe it wouldn't have formed on Earth. Maybe it would have formed on Mercury or Mars or something like that. These are other arguments, okay? And maybe you've got a point. But here's what I want to get to. So let's say that, let's do this. Let's look at a dial. Do you know what a... This is do you know what I mean? Like a dial, something it turns. You know what I'm talking about? On your,
Like your stopwatch
radio.
at home. So you do your timer.
Right. Or you turn a volume button or a volume knob on your car. So it's something you turn. Okay. We're going to call this. We're going to call this the C1, and that means constant. It means a number. Well, or maybe instead of C, let's just use the word N or the letter N and just say N for number 1. Okay. And this is that ratio of gravity to electricity, which we just talked about, right? And we already figured out, now whatever that number is, this is the one that's just right. This is where it's at right now. But what if you could just take that dial and you could just change it by 1% or 2%. We already mentioned that if we make it too big, then the sun engulfs the entire, solar system, and also it's really dark. It doesn't put out a lot of energy. But if we make it really small, then the sun is tiny and it burns up all its fuel really fast. Okay? So this is just one knob that I'm going to do. Like, pretend I'm God right now. Pretend I'm God, and if I could just turn this knob and adjust it, what we find is that this is we're going to call this the value that it currently is. So this is, I'll call this the real, why is that in writing? I'll call this the real number, okay? That's what it actually is, or the actual number, what it is right now. And these are a whole bunch of other numbers that that God can dial that number to. And let's say that there's a small range, a little range right here, where if we dial it between here and here, life can still exist, okay? But there's a very narrow range that it could happen. Like I've been explaining, if it's beyond more than this amount, life can't exist. If it's less than this amount, life can't exist. So it's a very small range. You got to finely tune that number in order to make it so that this ratio is just right so that life can exist. Is this making sense so far a little bit?
Yeah.
So first of all, isn't it sort of weird that this number, N1, happens to be in just the right zone for life to exist, for us to exist? Isn't that kind of interesting, right? Seems unlikely, right? Look how many other options. We could turn this knob, all the way over here. That'd be easy to do. It would be easy for God to do, right? We could turn it all the way over here, but life couldn't exist. We could turn it here, life couldn't exist. Turn it here, life can't exist. Can't exist, can't exist, can't exist, can't exist. Maybe can exist, does exist. Got it? So there's a very narrow range of that happening. So what's the likelihood that it just so happens that the actual number, the real number, is in that tiny little fine-tuned range? What's the likelihood of that? High or low?
Oh.
It's probably low, right? I mean, unless God intended to put it there, which is maybe the argument I'm making. But if you didn't intend it there, let's just say you were throwing darts, right? I just threw darts back here. And, of course, I'm a terrible dart player, so I never end up getting it in the circle. I always get it on the edges, right? So let's say I play a dart, lands there. Oh, life can't exist. Lands here, life can't exist. And it's only in this little narrow range that life can exist. So you'd think the likelihood of that happening would be pretty low. Are you with me so far? So already, I think it's kind of interesting that this particular number, N1, which may be the ratio of the gravitational force to the electric force, the electromagnetic force, already it happens to be in a very narrow range that allows for the existence of life. I think that's strange. Here's something stranger. Here's what's really strange. The standard model of physics says that there's not one number, N1. There's not 3 of them. There's not 10 of them. But there are 25 constants of nature that have to be measured. You can't derive them. They have to be measured. There's things like the ratio of the mass of the proton to the electron. Things like that. But there's 25 constants. So imagine, we don't have one dial, ladies and gentlemen. We have, here's N2. We have 25 of these dials. And every single one of them has to be in a very narrow range in order for life, as we know it, to exist. 25 of these things. Now, if God's doing it, sure, God could make that happen. That's part of the reason I believe in God. But if you just randomly chose these numbers, what's the likelihood that all of them, every single one of them, would fall into that narrow range of the number? Big or small? Pretty small. I'm going to give you an idea of how small it is, just an order of magnitude, how small it is. You ready? Let's say the likelihood of just of n1 randomly appearing within this range. What is it? 1 in 10, 1 in 20, something like that. I mean, we're just looking at it. Okay? Let's just say it's 1 in 10. It's probably much, much smaller than that. But we're just going to say that the number is 1 in 10 for n1 to have appeared in the right zone. We'll say the same thing for all 26 or 25 of them, okay? Well, the likelihood of that happening randomly, turns out, is 1 in 10 to the power of 25. Now, you don't know what that means, but I'm about to explain what that means. Here is how we do it. I have poured salt, 1 cup of salt into this container. Okay, ladies, do you want to pick out 1 grain of salt for me? 1 grain, not 2, not 3, 1. Every time they try to do it, 50 grains are sticking to their fingers. You got 1, okay. You see how tiny it is? Did you find 1?
Yeah.
You can barely see it, right? It's tiny, right?
Yeah.
It's tiny. You see it? Now, it turns out, take a look. Turns out there's a tiny diamond in here, the same size as one of those grains of salt. There's not really, but let's pretend that there's a diamond in there, the same size as that. Do you think that you'd be able to find that diamond in here? How about, better yet, how about if we blindfold you and you have to reach in and grab 1 grain of salt? Are you going to find that diamond? No. It's going to be pretty hard, right? It's going to be real hard. Now, there's about somewhere between 5 and 10 million grains of salt in this. Somewhere between 5 and 10 million. What if instead of this 1 cup of salt, I don't want you to find that tiny diamond in there. I lied to you. I actually hid that diamond somewhere in a beach. But it may not be at Dad's beach at Sarasota. It could be at any beach on the planet. So 1 tiny little diamond the size of a grain of sand, I've hidden it somewhere on a beach in the planet. You think you'll be able to find it? Yeah. All the grains of sand on the planet. The likelihood of finding that 1 diamond in all the grains of sand on the planet is nowhere near as small as this number. To get to this number, we have to have 1 million Earths. 1 million Earths lined up. That's right, 1 million of them. There's 1 tiny diamond somewhere hidden in the shores of the beaches of one of those million planets. If you can find that, 1 little tiny diamond, blindfolded, that is how hard it would be to fine-tune the constants of nature to create life as we know. Isn't that incredible? But it gets better. My estimation, I was being very, very, very rough about the likelihood of us being in a habitable zone of that parameter is 1 in 10. It's hard to do the calculations. You have to do simulations, and they're all a little bit different. But in reality, the likelihood of randomly choosing a parameter that works for each one of those numbers is probably significantly less than 1 in 10. So in other words, the number that I just gave you, where you have to be blindfolded and find that tiny little speck on the beaches of any beach of 1 million Earths, that number, that probability is probably way, 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 way too high compared to what we need to produce the constants of nature that allow for us to exist. And to me, that's very, very strong evidence that this was not an accident. That there was somebody turning these knobs to get it just right so that we could exist. The alternative to somebody turning dials to make this just perfect is a coincidence that is unbelievably unlikely. Now, I do want to get to a counter-argument. Is everyone still with me? You doing okay? Okay. Here is a counter-argument. The counter-argument by people who claim to be scientists is this. Well, there's no God, but what there are billions and trillions and quadrillions and sextillions and septillions of other universes where in each of those other universes, the dials are all different. So in other words, every possible value of n1, n2, all the way up to n25, every possible value of those exists in some universe. It's called the multiverse. I'm going to write this. It's called the multiverse. That means many, and then many universe. Actually, I won't end the quotes there. Multiverse, I'm going to say theory, and I'm going to keep this all in quotes. And the reason I keep it in quotes is because I'm going to argue that this is not a theory at all. It's not a scientific theory. So again, the argument is, well, yes, this is really unlikely to happen, but if you have tons and tons and tons of, or infinitely many universes, well, they all have different values, and they all exist, but we just happen to be in the one where it's just right? We just happen to have been created or evolved, or we happen to exist in the one that happens to be just right. But there's infinitely many other universes. That's their solution. It's called the multiverse theory, and I put it in quotes because it is not a scientific theory. It's not even a scientific hypothesis. It's not scientific at all. And the reason it's not scientific is this. The universe consists. I'm just going to draw a big circle. So here's the universe, and here we are. I don't know. The universe consists.
Is that Earth or our solar system?
It doesn't matter. The universe is that big that, it could be our galaxy right there. We are here. So this is the universe. The thing about the universe is that, what's the edge of the universe? Well, the edge of the universe is where light has gone. It's the furthest reaches of where light has gone. So in other words, anything beyond the universe is beyond what we can see, because light can't even make it back to us. If there was anything beyond the universe, you can't see it. Basically, by definition. So here's the problem with the multiverse idea. Let's say they claim that there are other universes out here, and every one of them has a different value for all those different numbers. But here's the problem. The reason it's not scientific. Science relies on being able to measure things, observe things. Measure, I think that's it. And then you can do other things, make inferences. You can't measure this.
Can't see it.
You can't see it. There's no possible way to measure it. So it cannot be measured, and therefore it is not scientific with this. So be very wary of any person who claims to be a scientist who tries to convince you this. The first response should be, what scientific evidence do you have for the existence of other universes?